The following table shows a number of daylight hours in Grand Prairie. In Part A, convert each date and time to a number that can be used for graphing. When we model a real-world situation with mathematics, it is often necessary to convert measurements, like dates and times, to numeric values that can be used for graphing and analysis. We can convert dates to day numbers using the following rules. January 1st is day 0. Dates in the previous year are negative. If no year is specified, assume a non-leap year. Let's look at the days surrounding January 1st. December 21st is 11 days back into the previous year, so we'll use a day number of -11. A consequence of assigning January 1st as day 0 is that all days in the future will be offset by one number. To account for this offset, remember to subtract 1 when calculating day numbers after January 1st. The calculation shows how we can get the day number for March 21st. There are 31 days in January, 28 days in February, and 21 days in March to get to March 21st. Subtract 1 to account for the January 1st equals day 0 offset. The day number is 79. The day number for June 21st is 171. The day number for September 21st is 263. And the day number for December 21st is 354. We have now converted all of the dates to day numbers. Time that is expressed using hours and minutes can't be used for graphing purposes. It must be converted to decimal time. "6 hours and 46 minutes is equivalent to 6.77 hours. Leave the hour value unchanged. Divide the minutes by 60 to get the decimal hour equivalent. 46 over 60 equals 0.77. This gives us 6.77 as the decimal hour. "12 hours and 17 minutes is equivalent to 12.28 hours. "17 hours and 49 minutes is equivalent to 17.82 hours. "12 hours and 17 minutes is equivalent to 12.28 hours. And finally, 6 hours and 46 minutes is equivalent to 6.77 hours. We have now converted all of the times to decimal hours. In Part B, draw the graph for one complete cycle. Bring up the table we completed in Part A. The day number, n, is the independent variable. It goes on the x-axis. The number of daylight hours, d of n, depends on the day number, so it goes on the y-axis. One year is 365 days, so the x-axis should have tick marks that will let us view one complete year. In this example, we'll use x min equals negative 50, x max equals 400, and x scale equals 50. Note that we should start at negative 50 instead of 0 so we can include the point with a day number of negative 11. There are 24 hours in a day, so the y-axis can be set to y min equals 0, y max equals 24, and y scale equals 4. Use the table to plot the points. Now draw the graph. In part C, write a cosine function that relates the number of daylight hours d to the day number n. Bring up the table and the graph. The minimum value of the graph is 6.77 hours, and the maximum value is 17.82 hours. Use the amplitude formula, A equals max minus min over 2. Plug in 17.82 for the maximum and 6.77 for the minimum. This gives us an amplitude of A equals 5.525. Now use the vertical displacement formula, d equals min plus max over 2. This gives us d equals 6.77 plus 17.82 over 2. The vertical displacement is d equals 12.295. The period is 365 days. The b value is 2 pi over 365. There is a phase shift 11 days back, so c equals negative 11. Plug the parameters into the general cosine formula, y equals a cos b theta minus c plus d. The independent variable is the day number n, and the dependent variable is the daylight hours d. The function is d of n equals negative 5.525 cos 2 pi over 365 times n plus 11 plus 12.295. Remember the negative since the cosine shape is upside down. In part D, how many daylight hours are there on May 2nd? Bring up the graph and its function. Find the day number for May 2nd. 31 plus 28 plus 31 plus 30 plus 2 minus 1 equals 121. Remember to subtract 1 to account for the 1-day offset. Recall that this occurs because January 1st is day 0. On day number 121, the number of daylight hours can be found by evaluating d at 121. In method 1, we'll evaluate d at 121 directly. Use 121 as the day number in our function. This gives us 15.86 hours. In method 2, we'll use technology. Set the view window to x min equals negative 50, x max equals 400, x scale equals 50, y min equals 0, y max equals 24, y scale equals 4, and draw the graph. Use second trace value with x equals 121 to get 15.86 daylight hours. This is the same result we obtained in method 1. Now we'll move on to part E. In 1 year, approximately how many days have more than 17 daylight hours? Bring up the graph and its function. We are trying to find the number of days the graph is above the line y equals 17. To find the points of intersection, we need to solve the equation shown. Plug in 17 for the number of daylight hours. Use technology to find the intersection points, 139.45 and 203.55. Subtract. 203.55 minus 139.45 is approximately equal to 64 days. Each year, Grand Prairie has approximately 64 days with more than 17 hours of daylight.